Swayam Prabha. Digital India. Educated India.
Hello. Today I'll discuss about Euler equation for turbomachinery, which is very important for energy transfer within the machines. I'll discuss today derivation of Euler equations, velocity triangle for turbomachineries, and illustration. And here I'll discuss about radial flow pumps and compressors. Regarding the Euler equation of turbomachinery, I like to say that in turbomachines, the energy is transferred either to or from a continuously flowing fluid by the dynamic action of rotating impedance. There is a change of angular momentum as the fluid passes through the impeller, imparting torque to it, and thus the Euler equation of turbomachinery will be derived in these sections that gives us the expression of shaft torque. Now, while deriving, I have considered a control volume surrounding an impeller. The control surface may be considered A from the rotor such that the property may be assumed uniform and axisymmetric. Thus, I have taken a control volume surrounding the impeller, and Z is the axis of rotation of the machines. And as I have told, control surface is taken A from the impeller so that the property is uniform. And let us consider C1 is the velocity that's entering the control volume at the point A, and C2 is the velocity leaving the control volume at point B. And let dm dot be the mass flow rate that is entering and leaving the control volume, and R1 and R2 be the radial distance at the point A and B, where Z is the axis of rotation. Furthermore, I, J, K be the unit vector in the direction of R, theta, Z, where R is the radial direction, theta is the circumferential direction, and Z is the axial direction along the axis of the rotation. Thus, I can express the velocity field C as I into CR plus J into C theta plus K into CZ. Therefore, I can write that momentum leaving the arbitrary control volume at the point B is dm dot into R2 into C theta 2. And momentum entering the control volume at the point A is dm dot into R1 into C theta 1. Thus, momentum flux out of CV is equal to dm dot into R2 C theta 2 minus R1 C theta 1. Hence, if dt be the torque on the fluid in the control volume, then dt would be equal to dm dot into r2 c theta 2 minus r1 into c theta 1. Considering possibility of several inputs and exit, I can write torque on the control volume. Again, I repeat, considering the possibility of several inputs and exit, we can write torque on the fluid in the control volume T is equal to sigma dm dot into rc theta 2 minus rc theta 1. Torque on the impaler would be opposite to that of the fluid. So T on impaler can be written as sigma dm dot within the bracket r1 c theta 1 minus r2 into c theta 2, which is positive for a turbine. If omega be the angular speed of impeller, then the work done on the shaft per unit mass flow rate can be written as omega into r1 c theta 1 minus r2 c theta 2. So that can also be written as u1 c theta 1 minus u2 c theta 2, where u is the peripheral velocity of the moving blade and 1 refers as inlet and 2 refers at exit. Thus, the work done per unit mass for compressible flow is given by, if you take a turbine, it will be u1 c theta 1 minus u2 c theta 2 would be equal to Cp into del T0, where del T0 is equal to temperature drop across the impaler. For a compressor, it will be u2 c theta 2 minus u1 c theta 1 is equal to Cp into del T0, where del T0 is equal to temperature rise across the compression impaler. For incompressible flow, work done per unit volume would be given by, for turbine, it will be multiplied by rho and would be equated by del P0 for an ideal situation, where del P0 is equal to pressure drop across the impaler, and for an actual situation it will be divided by eta h, where eta h is the hydraulic efficiency. So for actual case, in considering a turbine, it will be rho into u1 c theta 1 minus u2 c theta 2 divided by eta h equal to del P0, where del P0 is the pressure drop. Similarly, for the compressor, it will be rho into u2 c theta 2 minus u1 c theta 1 is equal to del P0 in an ideal case without loss, where del P0 is equal to ideal pressure rise across the impaler. In actual situation, it will be multiplied by eta h. Now the work done per unit weight can be expressed as, for a turbine, u1 c theta 1 minus u2 c theta 2 divided by g is equal to del h in case of ideal flow. So with respect to the earlier expression, it has been divided by rho g, and in case of actual flow, it has been divided by eta h, and the corresponding relation for the compression would be u2 c theta 2 minus u1 c theta 1 divided by g is equal to del h in ideal situation. Del h is equal to head rise across the impaler and in actual case it will be multiplied by eta h. What is very important that this expression is valid both for compressible and incompressible flow, because this above expression is independent of rho, that's density. I like to discuss another important concept is the velocity triangles for turbomachinery, which is used for the design and analysis of any turbo machines. The velocity triangle shows the vector relations of all relevant velocity components, including relative, absolute velocity, and the blade speed at any point within the machines. Thus, at any point within the blade passage, one can say as relative velocity plus blade speed is equal to absolute velocity. Note that this is a vector addition. Thus, W bar plus U bar is equal to C bar, where I have used the following notation: C as absolute velocity, W as relative velocity, and U is the peripheral velocity of moving blade, and one inlet to the machine and exit 2 is the exit to the machines. I'll use the following notation. The important point here that from velocity triangle we get W plus U is equal to C. It's a vector addition where W being the relative velocity, U is the velocity blade speed, and C is the absolute velocity field. Now our notation is C would be always used for absolute velocity, W will be used for relative velocity now and onwards, U is the peripheral blade speed, 1 would be used at inlet to the impeller, and 2 will be exit from the impeller. I'll give some examples illustrating use of velocity triangles for radial and axial flow machines. To initiate the discussion, I have taken radial flow machines, and it's a compressor or pump. This is a schematic of a backward flow radial machines where I have shown the meridional streamlines, and I have also indicated the direction of rotations, and I've indicated plus and minus sign illustrating high pressure side and low pressure side of the blade. So you can understand by the direction of rotation. So you need to push the fluid against the high pressure side, and thus you need to add the energy from the outside. So it would be a compressor or a pump impeller. Now B2 is the width of the impeller, and D2 is the outer diameter, D1 would be the inner diameter, right? With this geometrical parameter, let's go to the velocity triangle in the next page. Now I have illustrated here the velocity triangle of backwardly curved fin impeller, which is either compressor or a pump impeller. Here I have considered that inlet swirl is 0, so there is no inlet swirl. C theta 1 is equal to 0. So if we consider the inlet velocity triangle, it will be U1 plus W1 is equal to CR1. CR1 would be equal to C1. That's equal to Cm1, which is the meridional velocity connected to the flow through the machine's volume flow rate or mass flow rate to the machine, whatever you say. Now further, exit velocity triangle would be W2 plus U2 is equal to C2. Look, W1 and W2, which is the relative velocity, follow the blade curvature. And note again, I am following the rule that W2 plus vectorically, if you add U2, then you will get C2. So first I'll have to draw the inlet and exit velocity triangle to analyze something further regarding head developed by the impeller. Furthermore, let me explain you that there will be boundary layer growing on the blade surface, and because of the boundary layer growth, there will be a blockage, and so I have taken a blockage factor K here. Furthermore, since it's a compressor or a pump, flow has to decelerate. So W2, the relative exit velocity, will be less than W1, and thereby P2 will be greater than P1. Furthermore, CR2 will be Q divided by K2 pi R2 into B2. R2 is the exit radius and B2 is the width. K2 is the blockage factor, which is greater than 1. And at inlet, you can find out Q is the flow rate, divided by K1 into twice pi R1 into B1. K1 would be approximately equal to 1. Since the blockage, because of growth of boundary layer at the inlet, will be much less compared to the exit. Furthermore, the head developed would be H U2 C theta 2 minus U1 C theta 1 divided by G. Now head developed would be maximum when C theta 1 would be equal to 0. Now in this case, I have drawn the velocity triangle without swirl, inlet swirl. So here in this case, particularly head developed would be U2 C theta 2 divided by G. Hope you have understood the velocity triangle, at least for a radial flow impeller. With respect to radial flow impeller, we often find the three kinds of curved vane. One is named as forward, radial, and backward curved vane. Now this name is given with respect to the rotation. Suppose, look, in all these three cases, rotation, direction of the rotation remains the same. So with respect to the rotation, the curvature is backwardly moved. So it is named as backward curved vane. This is radial. And this is with respect to the direction of rotation is forwardly curved. So it is known as forward curved vane. So please, again, I like to tell this backward, radial, and forward curved vane is named with respect to the direction of rotation. Now again, look here. Consider the three impeller having the same outer diameter and they are rotating at the same speed. And otherwise, other parameters are the same. So what I like to tell, value of the exit relative velocity is same in all the cases, and u2 is same, being it is rotated with the same omega and having the same diameter. Now if we draw the velocity triangle, we'll immediately appreciate the c theta 2, what is the swirl at exit. The value of swirl at exit would increase as you move from backward curve to forward curve vane. Please appreciate the velocity triangle, that it is always u2 plus w2 plus u2 is equal to c2, and projection of c2 in the tangential direction will give you again I am telling, projection of c2 in the tangential direction will give you c theta 2. Similarly, projection of w2 in the tangential direction will give you w theta 2. So what are the characteristics of this? Immediately from the velocity triangle, I can appreciate that work capacity increases with c theta 2, and thus its maximum for forwardly curved vane and minimum for backwardly curved vane. Further, please note that forward curved vane has a steep operational characteristics, higher noise level, and lower efficiency, so it is usually not used. However, forward curved impalers have a self-cleaning property which are often used in foundry. On the contrary, the backward curved vane have higher efficiency, lower noise level, and hence it is usually recommended. Now let us define xi. Xi is the pressure rise coefficient. Xi as del P0 by rho U2 square. So xi is the non-differential pressure rise coefficient, and similarly phi is the flow coefficient. It's written as CR2 by U2 here. With this definition, we can further move as, here I have indicated xi phi characteristics for a backwardly curved vane, radial vane, and forward vane. This is for backwardly curved vane. Here you can see xi decreases with respect to phi, whereas for a radial vane, xi remains invariant, and for a forward curved vane, xi increases with phi. So if we consider power, for these two cases, power increases with phi. However, for backwardly curved vane, power does not go beyond a certain limit. So this is very important characteristics for a backward curved vane. Now I'll take you a complete different directions, that's effect of compressibility for a radial impeller. If we consider a compressor and a radial flow machine, and if we consider the flow is compressible, then we always try to avoid formation of shock within the blade passage. Why? Because shock formation involves additional losses. Furthermore, please note that the sonic velocity is proportional to root over T. And at inlet, temperature is lower than the exit. Thus the sonic speed at inlet is less than the exit for a compressor. Thus I have written in the next slide as, by controlling Mach number at inlet, we can assure that shock formation may not occur within the blade passage. And I like to tell you one thing, that inlet is more critical than exit. And we always try to limit that inlet Mach number does not go beyond a value of 0.8, so that there would not be a chance of strong shock formation within the blade passage. I have shown here a inlet velocity triangles with and without positive pre-wheel. That means I am telling you how I can control inlet Mach number for a compressor. Look, W1 is the velocity, relative velocity without a pre-wheel, and W1, again I have shown another triangle with pre-wheel. Hope you will appreciate that with pre-wheel, W1 is less than the W1 without pre-wheel. So what we'll do? We'll make an arrangement with providing a guide mate or inlet blading curvatures, so that there exists some free will at inlet which will reduce the inlet Mach number. However, one should know that work capacity would also decrease because of C theta 1. Thank you for listening.